welcome everybody to the afternoon session. Since we have the Greek night tonight, let's be on time. And our first speaker will be Andrzej Sitarz, talking about spectral metric and Einstein fractionals.
Okay, thank you very much. It's a great pleasure to be here in Corfu and talk to you about something, which is also a slightly different approach to non-commutative geometry, more in the line of what Walter was talking about yesterday. And this is a joint work with Ludwik Dąbrowski from CISA and my student Paweł Zalewski. The general idea is that whenever you hear the talks here about non-commutative structures, quantum space-time, and all this, I mean, there's a lot of mathematics involved, which is, I just singled out a couple of keywords like Hopf algebras, Sitarz algebras. K-theory hasn't appeared yet, but this is also a part that has some applications. And then you have those ideas about quantum gravity, what is a quantum space-time, deformation quantization, Poincare, whatever your favorite deformation of Poincare algebra or Poincare group, anything, Moyal deformation, and of course, Kappa deformation, which is one of the most favorite deformations, which keeps a lot of symmetries preserved and has some sort of a nice real approach, to things, to questions that you can pose in physics. But, all these approaches and many of those approaches, are something like coordinate based in the sense that they're given by relations, by some generators, so to say, and relations. And the real question, is, what does it really represent? So what is the notion? What is the unifying notion of what's the non-commutative space or non-commutative space-time? And finally, of course, whenever we want to construct something physical out of it, how to get some numbers. Numbers, not necessarily in terms of, real or complex numbers, but numbers in terms of functionals. So functions, functionals. So really something that you can compare with the measurement in the very end. By the way, the thing in the background, what you see is a sort of artist impression that's been proposed by Matilde Marcoli, artist impression what a non-commutative space is. This is done by Pollock generators or something like abstract thing. So we cannot really visualize what non-commutative spaces are. We only can describe it by some algebraic notions like relations or operators on Ham-Hilbert space. Now, my talk would be how to get numbers and something how to get absolutely, feasible and geometrical numbers. So things that do have a meaning in geometry. So this is, the question that has been also, advertised and posed by Walter. And this question goes back to the first half of last century. Namely, can one hear the shape of a drum? So what is the information that is encoded in the operators, like Laplace operator, like Dirac operator, so any differential operators? And we know, coming from the other side, that, the way you construct the Laplace operator involves a metric. So if it involves a metric, then it involves all the things that are hidden in metric, like for instance, Riemann tensor, Ricci tensor, scalar of curvature. Now the question is, how to get it back. So imagine you have an operator which is, God's given, or, you just know only the spectrum of this operator. And of course, what is the way, to retrieve, I wouldn't say all, but some relevant geometric information. And of course, coming back to the question, can you hear the shape of the drum? We know, and that was also advertised. That was also described by Walter, that the answer is no. And there are very nice examples, also for manifolds, closed manifolds, but also manifolds with boundary, which he showed a picture of. But nevertheless, it appears that some things that we know in physics, like the action functional, they are actually part of the spectral data. So it might be that, of course, the mathematical answer to this question, can you hear the shape of the drum, is of course no. But maybe the physics that we know, the physics of fundamental interactions, actually depends only on the spectrum, is really spectral. And now, of course, what is the tool, the main tool to get, this information? And this is actually, you know, so Mark Katz is here, but the tool is basically due to these three gentlemen. This is Harry Zilli, Peter Gilkey, and Bryce DeWitt, Gilkey-DeWitt coefficients, which come from the expansion, so-called asymptotic expansion of a very simple thing, so namely the Laplace operator. So imagine you have a Laplace operator, which is an unbounded operator on a Hilbert space. So imagine it for a sphere or for a circle. I mean, it has growing eigenvalues. But of course, if you do the a very nice trick, so you take the exponential with minus t is positive, and this Laplace operator, you get something which is of a trace class. So you can sum up the eigenvalues. And when you sum up the eigenvalues, you get a number. I mean, this is just the usual regular trace on a Hilbert space. And the thing is that when t goes to 0, it explodes. So it's really degenerate in t. But the thing is, the very nice feature, and this is, you know, the result of this three gentlemen, is that you can make an expansion, so-called asymptotic expansion in the powers of t. And of course, if you see it, I mean, it starts with n being 0 and d being the dimension of the manifold. So if 0, this starts with minus d over 2. So it really is something singular at t being 0. Nevertheless, you know, those coefficients depend only on this operator, only on the Laplace operator, and they carry a very important geometric information. So they carry the information about the volume, they carry the information about the curvature of the manifolds, so curvature of the metric, and so on and so forth. And this is one thing. The second thing is they are computable. So if they are computable, so we can, by computing them, we can retrieve this information. Okay, so what you have in the background is, you know, something which is the ISIS geometry, which I will be talking about is torus. And of course, you know, I don't know if anybody recognizes what is the spectrum. This is the spectrum of one of the elements. And what we'll be trying to retrieve some information about the curvature, a little bit more of a torus, and also non-commutative torus, which is a very fine example of a non-commutative manifold, just from the spectral data. All right. I said that the tool is actually hit kernel expansion, hit trace expansion, but there's a very nice refinement of that. And this is due to this gentleman, Mariusz Wojcicki, and then it's been used later. I mean, also the hit trace and the Wojcicki residue that's been used later by Alan Kohn and Ali Chemseddine to construct something. I mean, the more systematic way to get an action out of the data they construct, so Dirac operator, algebra, and Hilbert space. But I mean, for the manifolds, and also, you know, for the generalization of manifolds, this notion of Wojcicki residue is very, very useful. Why? I mean, it generalizes something like a trace on a suitable algebra of operators, which includes this algebra of operator. This includes the operator like Laplace operator, for instance, or the Dirac operator, or any operator of this type, differential operator on a, say, vector bundle, on sections of a vector bundle. But also you need to extend this algebra to incorporate the inverses, so say formal inverses of these operators. And this is the algebra. The algebra itself is called the algebra of pseudo-differential operators. You can make it, you know, it could be understood as functions on a cotangent bundle of a manifold when you're talking about a manifold. And then, I mean, there's a very nice formula. So if you take homogeneous symbol, so symbol which is homogeneous in this, I mean, X is a point on a manifold, psi parameterizes the cotangent space at point X on the manifold, and we can just, you know, split the symbols into formal sums of things that are homogeneous of certain degree in psi. And if you take the part of the symbol, so the part of the operator which is homogeneous of degree minus n is the dimension of the manifold from now on, then actually if you make a very simple computation. So you just compute the integral over the sphere in this variable, which is the cotangent one, and integrate over the manifold, you get something which is a number, and the great, so to say, result, and that was in the 80s by Mariusz Wojcicki, also independently by Guillemin, but it comes back to the idea of Manin, to some extent the earlier idea of Manin, who did it for one-dimensional things. This is a trace. So there is a unique, and moreover, I mean, the trace, I mean, is very nice, but it's a unique trace on this algebra of pseudo-differential operators. And it happens that all the things that you can recover, you can also recover, I mean, both from the heat trace, but using a Manin transform, you can transform it to the Wojcicki residue. So, for example, you know, the Weil's law, which was also recalled by Walter, I mean, tells you that the growth of the eigenvalues of the Laplace operator gives you the information about the dimension of the manifold, but also about the volume of the manifold. We're talking about closed compact manifolds like a sphere or a torus or whatever, you know, your favorite compact manifold. So you can get it from the heat trace, you can get it from the asymptotics of the eigenvalues, but you can get it also from this Wojcicki residue. So imagine you take just a Laplace operator. For simplicity, we take the manifold of dimensional, even dimensional, so dimension 2m. This simplifies things. I mean, you don't need to take, you know, square roots. And imagine you take just the Laplace operator to the dimension minus m. So something like the inverse. Of course, I mean, you can always ask the question, I mean, what happens if there's a kernel of the Laplace operator? But the kernel is always finite dimensional space, so you can always correct it, you can neglect it. So you take this operator to the power minus m. So this is like a differential operator, but of order minus n. So the something like well, the inverse of minus n of a first order differential operator. And when you compute the Wojcicki residue of that, you get a universal constant, which is proportional to the volume of the sphere in dimension n minus 1, and the volume of the manifold m. So, okay, we get information about the volume, and this is the total volume. But I mean, if you want to have it as some sort of a refined information, so what is the volume element at the point? So you know how this is distributed along the manifold. So what is the measure which is related to the metric? You can consider a functional. So if you take f is a function on a manifold, so you can consider the following functional. So to a function, you associate the Wojcicki residue of f times this operator, negative order operator, and then what you get in the end, just the integral of the function with respect to the measure associated with the metric. So this is, you know, imagine, I mean, the function you can localize, you can make it almost like a Dirac delta function. So basically, then you can get the information what happens at one point. All right, this is, as I said, this is related to the asymptotic behavior of eigenvalues of the Laplace operator. So this is the first thing that, you know, has been known basically, you know, since the early years of 20th century. What happened next was, and that was also, you know, used very much, you know, done in the 60s and 70s, and then later, I mean, there was some application in the 80s using the heat trace. I mean, what is the next thing? So what happens if you, for instance, compute the Wojcicki residue, but not of the Laplace operator of the order of the power minus m, but minus m plus 1. By the way, if you go to the, so let's say, powers like minus m minus 1, you would always get 0. So that would always be 0. So there's nothing, you know, earlier that you can get. The first thing is the volume. So what do you get here? And this has been known from the Zilli-Gilkey-DeWitt coefficients, and that's been used also in the 80s, you know, to get some ideas about gravity actions and modifications of the gravity actions with torsion and other things. But basically, what you get is something which is proportional to the integrated scalar of curvature. So physically, this is relevant because this is the Einstein-Hilbert action. So this is why I was saying that the Einstein-Hilbert action, for instance, is really spectral. I mean, because this could be retrieved from the spectral properties, and through the Wojcicki residue, this is computable very nicely, of the Laplace operator. So this is something that you get. Of course, the integrated scalar of curvature is, again, I mean, this is very nice as an action functional for physics, but you know, it doesn't give you the information about the scalar of curvature at each point of the manifold. But nevertheless, you can go on, I mean, using the same trick, consider it not as a just, you know, thing that operates on Laplace operator alone, or the suitable power of the Laplace operator alone, but treat it as a function alone functions. So if you take a function f, function on a manifold, smooth function on a manifold, and you compute the Wojcicki residue of this guy, then you get the integrated function with the scalar of curvature. So again, making the function localized, you can get the information, what is the scalar of curvature at this point. Now, this has been done independently by, I mean, explicitly computed in the 90s by two groups. So first was Daniel Kassler from Marseille and Klaus Walzer from Mainz. And that's been used later on, you know, for the construction of the spectral action in the concept approach to non-commutative geometry, and getting also other terms, because, I mean, I did it, you know, I presented the result for the bare, so to say, Laplace operator, but you can always think of a Laplace operator that, you know, is somehow decorated, has some connection inside, and then you can see what happens and what are the next terms, because, I mean, here I computed it for minus m plus 1, you can think what's minus m plus 2, and so on and so forth. Sorry? Oh, yeah. It's known. It's expressed through the squares of scalar curvature, Ricci tensor, Riemann tensor, I mean, Weil tensor square, basically. In this thing, when this is just the pure Laplace operator, when you add the connection, the interesting term that appears would be the Young-Mills term for this connection. So this is something interesting. Now, oh yeah. I will come to that point. Yeah, this is, of course, Euclidean Riemannian geometry. Yeah. I will have a comment about it at the very end. I mean, there's a very recent paper which actually, I mean, computes things using the heat, sort of methods of quantum field theory for the heat trace. I mean, this is Wojcicki residue heat trace you can exchange. I mean, sometimes one thing is much better, sometimes the other, which could be applicable for the Lorentzian manifold. So I will mention that in the very end. So there is a hope. Okay, so now the question is, of course, we are very happy that you can get the information about the scalar of curvature, but of course, this is not everything. I mean, what we really want to know, and especially when we want to have something like equation of motions and have, in the context of gravity, the Einstein equations, I mean, we'd like to have something like Ricci tensor or Riemann tensor. So the question that we posed ourselves was, how can one retrieve the information about the, so to say, finer things, which are tensors, not scalars? And I would basically, you know, present you the results. And the result is that you can compute two functionals, and these functionals will be the functionals, of course. I mean, here we presented over vector fields, but you can do it also on differential forms. So, of course, vector fields you can also view as differential operators on a Hilbert space. I mean, just like Laplace operator, these are first order differential operators. So imagine you have these two vector fields as differential operators. Other words would be the derivations on the algebra of smooth functions. And when you can construct two functionals, the first functional would be just, you take the Wojcicki residue, VW Laplace operator to the power minus m minus 1. So why this is minus m minus 1? Because that would be of the order twice that, negative. This is first order, this is first order. So the total thing would be of order minus n, so minus 2m. And actually, when you compute it, this is actually very, very easy. You get nothing else but a metric. So if you're thinking about a metric, you can think of metric like distances, but you can also think of metric as a metric tensor. And metric tensor is nothing like a function of vector fields, on pair of vector fields. Okay, metric is one thing, but then if you go to the next order, so if you compute what is the Wojcicki residue of VW and Laplace operator to the order minus m, what you get is the Einstein tensor. So there's a way, spectral way, purely spectral way, and this is why, you know, basically it's Einstein meeting Katz. You can retrieve the information about the Einstein tensor just purely using Wojcicki residue, or also, I mean, by Mellin transfer, you can relate it to the certain coefficient of the heat trace expansion. All right. What is the tool? Basically, I mean, I will skip this part. I mean, this is something, you know, very technical. The tool is the pseudo-differential calculus, so the algebra of pseudo-differential operators, which are homogeneous, the rules, and I mean, technically, you know, to prove these theorems, you need to use specific coordinate system, which is quite convenient. So basically the normal coordinates, because then, you know, in the normal coordinates, you can express everything using geometric notions like the Riemann tensor. So I just skip the proof because this is just, you know, technical thing. What I would like to advocate also is that, you know, you can go much beyond that. So for instance, I mean, you know, Laplace operator is something that acts on the square summable functions over the manifold. So this is basically scalar, but you can think of a vector bundle. You can think of lifting, you know, the Laplace operator, lifting the vector fields to the vector bundle. How do you lift it? Well, simply using a connection. So imagine you have a vector bundle, you have vector fields, and you lift those vector fields to a connection on the sections of this vector bundle. And then, well, what happens if you compute? So you lift, of course, you know, the connection. You lift, also, of course, also the Laplace operator. So what happens if you compute it just like that for this case? And the answer is that, well, with the metric, nothing changes. With the Einstein tensor, so this Einstein function, you get the usual thing, which the only difference is that it's the rank of the vector bundle appears, but you get a second term, which is the integrated trace, I mean, this sort of contraction of the vector fields with the curvature of the connection. So this is something that appears. And I mean, this somehow relates, you know, to the fact that in the next term, I mean, of the just usual spectral action, I mean, the connection appears, and that would be the angular section. So here you see it, I mean, this is linear in the connection. So usually, I mean, this is something, you know, very, very trivial. Anyway, that was for the vector fields. But of course, you know, since the aim is to go to non-commutative geometry, and we already know that for non-commutative geometry, the notion of vector fields is slightly, you know, not well defined. I mean, you can think about derivations on the algebra, like the vector fields are derivation on smooth functions over a manifold. But of course, there might be no derivations on the algebra. There might be twisted derivations here in the case of kappa deformation, for instance. So much better notion are differential forms, because for every algebra, you can create a differential graded algebra, and you have first order differentials, and well, actually you can have too many of them, too much of these. But I mean, for instance, if you have Hopf algebra, which has symmetries, you may strict the things that are covariant or bicovariant. So, of course, you know, how, so the first question is how it can be done for the manifolds. And of course, you know, the thing is, I mean, here everything is spectral, so you need to work with the representation. So you need to, basically, you need to have a representation of differential forms on sections, on sections of some vector bundle. And of course, this means that you need to have a spin C structure at least. So you need to have Clifford algebra. You need to have representation of the differential forms as Clifford operators. All right. So again, you know, making the story very short. So imagine you have two differential forms. So V and W are just one forms. V hat and W hat are the images in the Clifford bundle. So this is the Clifford multiplication by the differential forms. you take the Dirac operator. Why the Dirac operator? I mean, it's a little bit more convenient to work with the Dirac operator. Once you have spin C structure, you have the Dirac operator. And you can also work with the Laplace operator, but Dirac operator is a little bit more convenient. And then what happens is that you can have these two functionals. So first this metric functional, and second is this Einstein functional. And this looks like slightly anti-symmetric, but actually, I mean, it doesn't matter. I mean, one can prove that it doesn't matter which order. So those two things are just the same. So it's not like, I mean, there's some sort of asymmetry between those two things. And again, you know, the result is that, you know, up to the coefficient, which is just the rank of the spinor bundle, I mean, what you get the metric functional and you get the Einstein functional. So there's a way to retrieve just from the data, like the Dirac operator, Clifford algebra, Einstein tensor, and metric tensor. So these are the classical results, but then you can pass to your favorite non-commutative example. And okay, why we've been interested about those non-commutative toric manifolds, so non-commutative tori. I mean, just to remind you quickly. Oh, because I mean, I need to represent the forms as bounded operators on a Hilbert space. So basically, this is, so the Hilbert space are the sections of the spinor bundle, and then, you know, the Clifford multiplication, I mean, just presents the forms as bounded operators. All right. So non-commutative tori manifold, so non-commutative two torus is something you can imagine generated by, I mean, by two unitaries that commute up to a phase. So UV is a phase VU, and this is like the implementation of the canonical commutation relations, the wide form of the canonical commutation relation. So, of course, I mean, there's nothing, this is nothing like a manifold in a classical sense, so we need to use this language of spectral triples that Walter was saying about. So you need to use algebra, its representation on the Hilbert space, and a suitable notion of what the Dirac operator is. And then what we can do, we can just, you know, try to compute again those two functionals. So what we do it for, I mean, we did it for the, also for the Laplace operator alone, because this is also possibly there's a notion of Laplace operator for them. And of course, you know, the flat Laplace operator, so the usual one, like the one that everybody, you know, takes for the non-commutative torus, or also for the moyal, just the flat Laplace operator would be boring, because flat means, you know, everything vanishes. So what we did, I mean, we took something that's been studied, you know, throughout recent years, namely something which is conformally rescaled operators. Why this conformally rescaled operators? Because this is a very nice class. I mean, for two-dimensional things, this is a very nice class of, so say, generalized metrics. And for instance, I mean, if you take moyal, you take the flat Laplace operator on moyal, and you rescale it like that with a suitable rescalement, you get a sphere. So you can have you can have something like a moyal sphere, something like a Fubini study metric, also for the moyal case. This is possible. So what do we get? I mean, the metric, I mean, this doesn't really, I mean, you get a result what the metric is, and basically the metric is just, you know, proportional to trace of the scaling factor. Tau is a trace on the algebra of non-commutative torus, so like the integral over it, and to suitable power of this scaling factor. But the interesting result is when you compute the Einstein tensor, it vanishes identically. Well, this is no surprise. I mean, this is a two-dimensional manifold. I mean, in a classical case, for two-dimensional manifold, that should be like that. It should vanish. So it simply means that the notion is robust, and when you go to non-commutative situation, it still vanishes. And of course, I mean, we did it also for the Dirac operator. You rescale the Dirac operator. This is, since the Dirac operator, I mean, here you need to rescale by k. So it's related to this h, to this h, basically it's like h square. So h would be like k square. And again, you know, the result is just the same. You get what is the metric, and the metric is quite easy. And you get that the Einstein functional vanishes absolutely identically. So you can say this two-dimensional non-commutative torus is just Einstein manifold, for instance. All right. You can go beyond that. I mean, this is just an example that you can do the computation. I mean, that was a sort of a, thing, because if you can compute it for 2 dimensions, you can compute it for 4 dimensions and just check that it's not 0. And this is the result. What is the metric and what is the Einstein tensor considered as functional over differential forms for the 4 torus. So the same situation, but for the 4 torus. I mean, this is just a formula, and you can just check that if you go commutative. So here, things don't commute. So for instance, this derivation of k doesn't commute with k, and this is the reason, there are so many terms. This is not very desperate. This is actually a formula that fits on a, one slide. But nevertheless, I mean, it presents that things are computable, even in an uncommutative case. So what is the outlook? And what are the things that could be done? And what is the, so to say, the benefit of that? So first of all, I mean, it's not really dependent on the, so to say, your model or your approach. It's the only thing, of course, you need to have. You need to have a presentation of your algebra, presentation or representation of your non-commutative model as operators on a Hilbert space. And the more important thing is you need to have something that defines the geometry. And what defines the geometry in this case, say Dirac operator, say Laplace operator. So this is something that defines the geometry. This is something that defines the metric. I mean, we're talking about the Euclidean case, but of course, this is it. Why? Because just giving you an algebra itself doesn't tell you anything. The algebra could be anything. I mean, if you consider, for instance, the algebra of functions vanishing at infinity on a plane, 2-dimensional plane, well, it could describe a plane. It could describe a sphere, because, I mean, you can compactify it. You add 1 point, or algebraically, you add a constant function. So you add a unit, and it just describes a sphere. So the information, the geometric information, is not always in the algebra and not in the coordinates. The geometric information is hidden somewhere. You could express it differently, like metric on something, but you can express it as differential operators. And once you have this generalized differential operators, there are tools to compute it using this non-commutative, this generalization, actually the generalization of the Wojcicki residue, or using the heat trace techniques. There are ways to compute it. So what is the benefit? You can compute something like an Einstein tensor. So you can study, for instance, and there's been, also, the question for many people in non-commutative geometry, what is torsion? So usually for gravity, we assume everything is torsion free. So now if you have a connection, how can you tell that the connection is torsion? So Levi-Civita connection, for instance, metric compatible. You can study, what the relation to quantum metric spaces. So the notion that was also, mentioned by Walter, the notion introduced by Riffel, that certain metrics defined by the Dirac operator on the space of states, I mean, is regular and sufficiently good. But also, there might be a way, classically or also non-commutative, just to access some information about singularities or orbifolds and so on and so forth, and also flat manifolds. But, non-commutatively, so imagine you have something which you believe is 2-dimensional. So 2-dimensional geometries, I mean, classically, they have vanishing Einstein tensors. So we can say that, okay, maybe some sort of conjecture that if you have a suitably regular spectral triple, so suitably regular non-commutative geometry describing something of dimension 2, and there are plenty of them. So you can have, for instance, this non-commutative tori, you can have some quotients of them. You can have, well, for instance, the Moyal plane, which is also 2-dimensional. You can have quantum spheres, and there are many examples of quantum spheres. So the conjecture is that, of course, with some regularity on those operators that you introduce, I mean, the Einstein spectral functional will be vanishing. Moreover, I mean, you can just make you can have something like the equation of motions. So, for instance, the vacuum equation of motion, like the Einstein tensor vanishing, would be the vanishing of Einstein spectral functional. And this I mean, mathematically, this describes what is something like an Einstein manifold, vanishing Einstein tensor, or the Einstein functional proportional to the metric function. So this is, plenty of possibilities. This is just a realm of everything. Now, there was the question, and I come back, to this thing. Of course, everything is Euclidean. Well, this is the drawback of that the spectral action that one has, I mean, is Euclidean, because, I mean, that's, because of the properties of the Laplace operators, properties of these operators. I mean, of course, you have no hope that e to the minus t Laplace operator for the Lorentzian geometry, so with indefinite metric, would be something like a trace class. But there are some ways to regularize it, and there are several approaches that's been tried. And more recently, there's a paper by Wrochna and collaborator about actually getting the first two terms of the spectral action, so this Zilli-Gilkey-DeWitt coefficient, generalizing it to the case of a genuine Lorentzian manifold, and this appears to be possible. And there's a hope that this could be extended, and there would be a systematic approach to the Lorentzian case as well. At the moment, the, so to say, attitude is that one does what many people do in different branches of mathematical physics. So computing things, say, in Euclidean case, and making whatever weak rotation or more systematic or less systematic to the Lorentzian case, or going the other way around if one needs it for quantum field theory. So at the moment, I mean, one doesn't know whether those two approaches would, so to say, lead to the same answer, but there is a hope, that the Lorentzian case will also be accessible. Now, the bottom line is just that this is a notion that is robust. So this is a notion that's applicable to classical geometry, classical Riemannian geometry, but you can extend it. And you can extend it, independently of your favorite model. The only thing, I mean, you need to have those tools, which are those functional analytic tools. And of course, you can do it for much, much more than I presented. I mean, for instance, I mean, the typical thing, that appears in the concept approach to physics, to the standard model, I mean, it's something like almost commutative geometries, and one can do it also and compute those geometric notions like the Einstein tensor or metric for them. So it's open, for exploration. So thank you very much. This is the reference to our paper. Thank you.
Okay, questions?
So, I mean, one possibility what you could do is you say there is no space-time non-commutativity. Take an ultrastatic, globally hyperbolic space-time and say only the spatial part is non-commutative, and then we do this and that. So that is one possibility to avoid talking about the Lorentzian setting. So that could work, or for a static space-time as well.
Yes.
Which would all, I mean, and that you could apply this to quantum field theory, and I think that would be also very interesting.
Absolutely. I mean, this is, so for instance, I mean, in a completely, unrelated thing, I mean, just, computing the spectral action for the standard model, this is what at one point, I mean, we did. And so we considered just the model with, so say, time, which just splitting, and considered static things. So when you consider static things, you're back to three-dimensional but Euclidean geometry. Nevertheless, I mean, you can still get terms and compare it with so say reality. So there are many ways to approach this question. So there are something like, well, very naive, a little bit more advanced big rotations. I mean, those static approaches there, and this sort of more recent approach motivated by and using tools from quantum field theory, algebraic quantum field theory. Yeah. So there's a way.
In algebraic quantum field theory, from what I understand, you have a net of polynomial algebras of type 3-1, which are interlaced. It's a net given by index by this net being causally complete regions. So one can describe the net from what I understand abstractly without talking about space-time at all. So you are somehow in a situation where something like the Gelfand-Naimark original theorem, but in a much more generalized setting. From what I understand, algebraic quantum field theory people, the conjectures are trying to recover space-time from this net. That would be, seems to me very, if it is can be done, it will be very intrinsic and very clear. Okay? One does not have to go through this Dirac operator approach at all.
The thing is that getting the space is one thing, but the part with the Dirac operator and the part with the or Laplace operator is about getting the metric. So this is like, I mean, of course, if you consider flat metric, I mean, you can forget about it. But getting the information about the metric and getting it, but also about the connection part, I mean, this is hidden in those operators. I mean, you cannot really consider, the metric, I mean, independently of the Laplace or Dirac operator. These are just, two faces of the same thing. So metric gives you the one of the operator or the other, and the operator gives you the metric. So whenever you think about the metric, but also, connections, then necessarily, those operators and this picture, I mean, should appear.
But here, one does not even get space-time. Space-time is put in somehow.
Well, this is like, I mean, the approach here is like, whenever you have a manifold, I mean, you have a metric and you can compute, for instance, Ricci tensor, Riemann tensor. So this is not like, for one space-time. You can do it for anything. So here, the model is that whenever you're given the data like an algebra that could describe your whatever quantum space-time or something, and you have the operator that gives you the geometric information, then you can recover the geometric data from this operator and the Hilbert space.
I understand, but it seems to me it is missing this original question of how to get space-time, which is differentiated. In this approach, suppose I have not given space-time, I'm just given some abstract data.
Yeah.
Like in the Gelfand-Naimark, you have a commutative Sitarz algebra. Here I don't know what the data is. Here the space-time is put in, it seems to me. And that has to be also emerged, in a more fundamental.
Well, I mean, this is the question, how things emerge. I mean, this is on the level how to so to say get the information about the space-time that emerges or space-time that you get. I mean, get the geometric information. So, for instance, you want to write Einstein equations of motion, or you want to understand the Einstein equation of motion in the context. So this is the way that puts it in a framework that's so to say model independent.
Any other questions?
So suppose you consider a fuzzy disk. Would you get also some contribution? The fuzzy disk.
Fuzzy.
Or the fuzzy sphere.
Yeah.
The fuzzy disk.
Yeah. The problem with the, this is one of the problems. I mean, with the fuzzy things or the finite things, that basically they are from the spectral point of view zero-dimensional. So this wouldn't work alone for the fuzzy sphere, fuzzy disk, or whatever fuzzy truncations. For that, you need to really work with the infinite dimensional Hilbert space because of the string. However, this is another question how you can approximate things, because we know that fuzzy sphere itself, I mean, is nice, but fuzzy sphere itself, I mean, it's nice only because in a way it approximates the real sphere, right? And this is also with disk or of tori or other objects. So the question is, and this is also probably related to this operator system and so talk water. I mean, how can one approximate these functionals in a suitable way for the finite things. And this is, also what Lisa Glaser has been doing, and also other people. And this is not an easy. I don't think there's a universal and widely accepted answer for that. How to approximate those functionals to make sense and to compute things in the finite setting.
Can you see some kind of boundaries?
Sorry?
Can you see some kind of boundaries in non-commutative spaces?
Some kind of
boundaries.
Boundaries.
Yeah.
No, the thing here was done for the compact closed manifold, so without boundaries. I think it would be. I mean, technically, it would be possible. I mean, you need to extend this to the differential calculus to the case with boundaries, which is doable, and do it. So possibly, I mean, here no boundaries, and that was the assumption from the very beginning. But I think, I mean, it is extendable.
Thanks.
All right, so let's postpone all other questions to the coffee break. Let's take our speaker. Yeah.
Thank you very much.
Thanks to Carlos Perez-Sanchez. Title change? The same. Only a younger Higgs matrix problem. Yeah, would be nice. So thanks to the organizers for the possibility to speak here and for organizing this very nice workshop. And so yeah, indeed, so the original title is only the first line, and the second line was just added when I realized that probably it's not the same kind of non-commutative geometry I have seen along the workshop. I should specify which this kind is. And I'm reporting on some works which I did in Poland, in Warsaw, and also in Heidelberg. And actually, the story begins in Krakow when I visit Andrzej, and he gave me a couple of comments which helped. And well, so I will talk about spectral triples, and it won't be extremely technical because I will talk only about finite dimensional ones. First, address some mathematical properties, and then to see the physical motivation this might have. And then I will move to matrix geometries, which can be seen as spectral triples. And then finally present some model that can be identified as Young-Mills. So, so as I said, I should say what I'm going to do, and this is differential non-commutative geometry, so to say. And let me roughly describe this as non-commutative topology to which you add certain metric data. So what's the first? The first is just basis on the base of this theory is Gelfand-Naimark's theory, and I mean the main result there is this equivalence. So sufficiently nice topological spaces are equivalent to unital commutative sister algebras, and here commutative is very important because you can just scratch this and do topology in this side. I mean, to work in this algebraic side and think that you're doing topology on the left-hand side. So that's a line of thought here. And what the metric data are, these are also based on spectra. And probably the first theorem there is, as already has been mentioned twice by Walter and by Andrzej, it's a Weiss law, again. So which tells you how fast the Laplace spectrum grows if you order this as such. And so if you put a threshold, then this asymptotically is this quantity, from which you can read off the volume and the dimension, for instance, of a bounded region on Euclidean space. And this led also Marek Katz to pose the question whether you can reconstruct the hot manifold, which from the spectral data, as we already have learned from two very nice talks, is impossible. And this is the counterexample. Well, first, Marek Katz's question was a very mathematically precise statement, but it was in the philosophy already the question whether you can reconstruct the form of a bell from hearing it. But okay, long ago. And the proof of these two regions is actually quite involved, and it's I mean, it begins with Milnor's 16-dimensional tori and some group representation theory by Sunada. And here's a typo, got and this made possible the construction of two isospectral non-isomorphic regions, which prove the negativity of this answer. But you can nevertheless hear the shape of a drum if you know a spectral triple. So this is, so to say, reconstruction theorem by Alan Kohn. And so this talk is in a little bit well, in the spirit of what you heard by Walter yesterday. So if this is music, then what they say is that they can hear an MP3, you truncate the spectrum, and you hear useful information, which allows you more or less to reconstruct your manifold. But it's also different in the technical sense I will be specifying later. So the thing is, you replace a manifold by other data, and this is a triple, and actually the two elements which are important here are the algebra and the Dirac operator, but they need a place to interact with one another, and this is a Hilbert space. In this case, since this is spin, you can just look at their interaction at the bundle, I mean, square integral spinors. So then if I replace this guy by this data, then I have to tell you how to recover this geodesic distance. Well, the procedure is known, and let me remind you that instead of just sending all the curves, you do the opposite thing. You send all the functions here given to fixed points between which you want the distance, and so to see what happens with the difference of the evaluations of these two states. So I mean of these two at this element of the algebra. So this gives you something useful once you put certain bound on the gradient of f, and this is more or less the Lipschitz seminorm. And then if you take the supremum, what you recover is precisely the distance you have on your manifold. And well, this fact is due to Kohn. Now this is important because when you try to generalize these two non-commutative algebras, then you are able to compute distance between states. So what's the physical motivation? I hope it won't be very polemic. And so well, this is a theorem which is developed in many stages, and so it states that the classical Lagrangian of the spectral of the standard model can be derived from spectral data. And the nice thing is that the input you need is quite modest. It's just a number of 3 generations of particles and certain algebra. So what is algebra? So now we are dealing with triples, and this algebra would be just the base of the of this new space. So you have to think of having begun with a Riemannian manifold, 4-dimensional, and then you extend in some kind of very mild way. I mean, you add extra dimensions in very mild way. Also non-commutativity in very mild way. And so this guy, okay. Once you put this in the machinery, then it gives you the Dirac operator, right? It gives you the classical Lagrangian of the standard model. Now the Dirac operator you have here. I mean, you introduce a new piece, and this might have also a Dirac operator because it's a triple. I just selected one of the screenshots in the proof, and this. I mean, I just like this because. At some point, you have a lot of actions which constrain your Dirac operator. We will see the actions, not in very detail, but okay. And this tells you that in this finite part of the algebra, the most general one is of this form. So these are zeros which have the right size for this to be a 99 times 99 matrix. And you have 96 because that's the number of particles you have. And the remaining non-zero matrices are just the analog of CKM and Pontecorvo, Makinagawa, Sakata matrices. Okay, this won't be important. Just the physical motivation is that this might have some usefulness in high energy physics. And the nice thing to see is that if you would have, if you had here a non-zero extra matrix, then you wouldn't be observing the standard model here. You wouldn't be obtaining the Lagrangian of the standard model, but all those zeros come from geometry. That's a sort of coincidence, which I liked. Now the theory is classical, fully classical. And so it's being pointed out by Marcoli and by Kohn in their book that it would be nice to have a quantum theory and to be able to compute spectral observables in this following way. So in path integral development of this theory. And well, it's not clear what to do here. First, let's be a little bit modest and scratch the fermions. Let's think they're integrated out. There was in the original statement, in the original question by them, also a certain projector, which is called D here, a certain constraint between this projector and the Dirac operator, and this plays the role of selecting the finite part of the algebra, so to say the matter content. So let's just think of this data as being integrated out and to deal with the effective action on the Dirac operator. And this will be defined later. So we're facing a paradigm shift from functional ill-defined integration over all metrics on a manifold. Let's say we want to do a random geometry. I'm making something's obvious, just like picking a Euclidean signature and also Riemannian manifolds. And so this is to be generalized to operate operational integrals, so integrals over differential operators. And this is, of course, for manifolds not too clear how to address, how to define. So so that's a motivation, and so a possible application, okay, in the long run is the related approach to Euclidean quantum gravity, let's say, via this thing that might be called random non-commutative geometry. Actually, it's random finite spectral triples in some way, but let's call it like the beginning. Other groups are referring to this as Dirac ensembles because obvious reasons you will see. So in the classical theory, you have a fixed background and you have 2 points, and then well, you compute propagators or transitions, probability transitions by summing over all the paths between them. Now the hard stuff conceptually and also technically in quantum gravity is that you have to make sense of the quantum superposition of these geometries. Let's say starting perturbatively, and then if you are more ambitious, then eventually you have to address also non-perturbative data. Okay, so that's only caricature. It's nothing done yet. So what's a spectral trip? That's I don't know. This I would like to think as think of matrix. For instance, think about the approach, the matrix theory approach to random surfaces, and what you do is summing over all possible triangulations. That's the way more or less what you can see. So some of the amplitudes it would be probably. So I'm summing amplitudes. I think. In the very same sense of random matrix theory, think about this being a Toft expansion of. Think about dimension 2 and about matrix theory. Then you have a Toft expansion of your action functional, of your partition function in N, in the genus, and that's what would be. Sorry. Well, it would be probably functions just of the Dirac operator, I would say. I'm happy. I don't know yet. So that's the aim. I'm not claiming I have this aim. I will claim only that I have a very small progress towards it. So the question to Fedele would be an amplitude sum. Okay, but it's not important. Okay, so what spectral triple is it consists of three items: an algebra, which if it comes from a manifold, then it's commutative, and it's represented as multiplication operators on this Hilbert space, and then you have a canonical Dirac operator there also, such that you have a boundedness of these commutators. So in fact, if you plug the coordinate functions, and what you get is the gamma matrices, and then you can start proving a lot of properties which are not so obvious and actually become quite relevant if you do, I mean, proper non-commutative geometry on a manifold. But this won't be relevant in this talk because I will restrict to finite dimensional settings. So these things are automatically satisfied. So what's the definition? Just what we learned from Gelfand-Naimark is just to scratch the word commutativity, and then well, the resulting structure is yes, precisely what you see here. Just an algebra represented on a Hilbert space, and okay, in which you have also a self-adjoint operator which satisfies these two conditions. And later on, when we address gauge theory, it will be useful to know what the space these gauge potentials will live in, and this is the space of cone one forms. Which is defined by this finite sum over this kind of commutators multiplied by a function. Now, what ensures we are doing geometry is the reconstruction theorem, which very roughly stated, because it has also an evolution in terms of actions. The actions were not always the same. States that commutative spectral triples are always Riemannian manifolds. Okay. So then, given a commutative spectral triple, you can always find a manifold such that, I mean, the given one has this origin. And just to, okay, since I'm telling something like non-commutative geometry, which is random, then I should specify that we are in a very small domain of this huge, discipline. We are constraining ourselves to spectral triples, which are finite dimensional and which, moreover, will be matrix geometry in the sense which I will introduce. So what's to do physics? You need some kind of action functional. In this case, so given a spectral triple, okay, I'm probably skipping many technical details, but that's why this is called toolkit. It won't be relevant in the finite dimensional setting I will be working on. So in the general setting, this is the physical action, and so here f is just a bound function around the origin, so which you can assume to be of the form of Laplace Stieltjes transform, and then you can apply the heat kernel techniques that Andrzej talked about. Okay. So you can compute Sealer-DeWitt coefficients and find some gravitational sectors you might recognize here. Now the aim is rather to do gauge theory, so you need some information about which the gauge fields are going to be. So, and the structure that helps here is just multiply Cartesian product of spectral triples, let's say. And so the base is just a normal manifold, and you can choose the finite piece, and according to this choice, you get a different gauge theory. This is very well studied, and so when f is a finite dimensional spectral triple, this is the product of these two spectral triples. So if you are aiming at applications, then to gauge theory, then what you need is also certain anti-unitarity. So here, which it's also again a little bit more complex to go into detail and satisfy certain actions of commutativity with D or anti-commutativity, etc. And the useful, let's see, the usefulness for this slide is that you can implement a write A action on H, and this allows you to implement an adjoint action. And so which are the connections here? Well, how do they arise in classical gauge theory or textbook gauge theory? It's just that you have an action functional which is invariant under a certain group. And this, you wish to do this global invariance local, and then what you do is to shift this derivative at certain object, which is one form there, and then in order to absorb this unwished term, so what you ask this guy to transform in this way under the gauge transformations. Now this looks in non-commutative geometry the following way: you take a spectral triple, well, my geometry, And if you have another algebra, so let's change the base algebra and generate new spectral triples, which I mean, Morita equivalence means which is the equivalent, Morita equivalent to the first algebra, which by definition means that you have certain A right module at least and B left module. Then what you can construct is new families of spectral triple. So the interesting thing, so this is the new Hilbert space. You replace the algebra, and then you have a possibility for several Ds. So the case that is interesting here for gauge theory is when A equal to B, and so Morita self-equivalence, and this gives you a tower, and this tower is indexed by certain things that are interpreted as gauge potentials or gauge or connections, let's say. Once you see which invariants are your spectral action is, and ask just as you did in this case to remain invariant. So, okay. So the main result is sketched in this slide, and so what is it? So this left panel is very well known. These are results by Connor and many collaborators, and also Walter analyzed pretty much in depth the gauge structure of these almost commutative manifolds. And so the thing is, if you propose certain new structure, you have to take care of this, how to transfer these results to the new structure, right? And that's the main result. So the thing is, the motivation, of course, to have finite dimensionality in these algebras, which will imply also that my Dirac operators are finite dimensional, is to be able to evaluate to deal with the partition function, to make it well defined. The harder way is to sort of get back in a extremely mathematically rigorous way, which I'm not claiming. So, but okay, let's see the usefulness of this object. So I replace then the base of manifolds by some matrix algebra I will define later, and what I find at this product of spaces is the matrix actually is PUN Young's theory. Okay, so that's the thing, and at all stages this obeys spectral triple action. So to put a little bit the thing in context of the Corfu workshop, so I should observe that the model I obtain is a little bit EKKT-like or BMN-like, but it's not the origin. String theory is not the origin. It's not also it's not the motivation either. But okay, and it's also related in the spirit to what Walter talked about yesterday. And also Federlizzi with Francesco Andrea and Giovanni Landi, they have a very nice paper which is related to von Seligman's result. And they analyze in depth the algebraic structure of these operator systems. They define certain tolerance algebras there. But okay, our truncations are not spectral. So let me first remind you what Walter did yesterday. So he takes they take smooth spin geometries of their starting point. For instance, for the circle, the theory is more general, but for the circle, it would be just take the Fourier. Well, you take the function and you convolute with a certain kernel. In this case, I just depicted this Fégé kernel, and this truncates your series, right? So what you get is no longer a spectral triple. You get a certain object whose substitute of algebra is rather an operator system. Now it's hard really even for the circle to go back here. And so this claim is in the Gromov house of sense. We are not doing this. We rather opt for, well, we didn't opt because actually it's more or less simultaneous development. So we didn't have options. And I did the following. So I just took a paper of Barrett, who actually is writing it, also addressing many, motivated by many fossil literature. here are some people of the conference I identify. I mean, hope they are all. And rather perform these algebraic truncations that have been very nicely described in the talk by Juraj. So what we do is to start here again and to perform this kind of algebraic truncations and get matrix geometries, which will be defined, sorry. And then there are results. I'm not claiming I go back, but there are people who do claim this. So the first and pioneered, this discipline was pioneered by Barrett and Glaser. And so they have certain numerical evidence for phase transitions here. And then there is also a group in Western University in London, Ontario, who also have certain evidence for phase transition, but it's still a one-dimensional thing. So there is no Gromov-Hausdorff way to come back here, which would be nice to address. Anyway, so that's more or less to put into context the thing. Let me talk about this at the final, if there is time, because I'm not sure how well I'm doing. Now, so here starts a little bit of sort of say precise, a little bit more precise language. So a matrix or a fuzzy geometry of certain signature. So it sort of suggests you can work also with Lorentzian stuff, but okay, then again, when you write down the path integral, it's not, at least not for me, clear what to do. So a matrix geometry is just a triple. Well, it's not a triple, but one can reduce after some theorems to a triple. And whose algebra is just a matrix algebra, and the Hilbert space here comes with a module with an action of the Clifford algebra of the chosen signature. And this is slightly different from the finite, the so-called finite spectral triples that were classified by Andrzej Sitarz and Mario Paschke. Were you? Yeah, and also diagrammatically by Tomasz Krajewski. And let's say they put nice diagrams here. The diagram is quite boring because the algebra seems simple, but the edge between these algebras is very robust. So okay, that's a non-trivial part because here, instead of giving you the 11 missing actions, I'm giving you just the theorem by Jean Barrett, which tells you the characterization of this kind of Dirac operators in terms of sums over products of, gamma matrices. Once you fix the convention, you know whether a matrix will be self-adjoint or skew-adjoint. And accordingly, you choose an anti-commutator with a Hermitian matrix or a commutator with an anti-Hermitian matrix. So it's a little bit cryptic. So let me give you just 2 examples. In the 1+1 description of what you get is this. So here is skew-adjoint and self-adjoint. And in the 4-dimensional case, it's been a little bit nicer because you get higher products. So this is a triple product of gamma matrices. And then, this is also usually interpreted as spin connection, but it's not being yet explored in full detail. So the observation I want to make here is that after you put this into the trace, what you will get is double traces. So you get matrix model, but always, but these matrix models come always with a double trace, which is pretty unusual in the random matrix theory, and then not immediate to address. So the thing is, you have to learn how to do this matrix. This trace, and well, it's just combinatorics here, what I did. Okay, it's just me. Let me point out that this diagrammatic stuff I used probably is not that stupid. Also people from the radar string theory use this, and actually it's more or less at the same time. So what I associate to this trace is just, for each one of these etas a chord, and then for each one of these crossings, a minus sign to the number of simple crossings, and then what I get from the traces just a kind of expansion in decorated chord diagrams, which is the sort of diagrams you see here. Well, the important thing here is not precisely the diagrams. This after you evaluate these, you just get integers here. It would be interesting to know this generation functionology of this thing. Probably these numbers are important. I don't know. But what I want to stress is that I mean, you get these traces from these two. I mean, this is the power set of 2T elements, and then you sum over all the possible partitions, and so some of the random matrices get inside, and some get outside, and you get double traces. When this partition is just the empty or the whole set, then you get the usual n scaling. You see matrix theory, and but the rule is the other, where you get double traces. But with this, you get already some kind of concrete realization of this kind of fuzzy geometries or matrix geometries partition function in terms of products of SUN and Hermitian matrices. So this Lebesgue measure makes sense there. And this PQ are just non-commutative polynomials. So there's a lot of free algebra here. And just to tell a couple of things it might be useful for, and so these things that appear in quantum gravity are not formal random matrices. They should be convergent random matrices, right? So that you can also interpret this in the formal sense. For instance, usually you get ribbon graph from vertices, and you would get hit color ribbon graphs in the case of two colors, two matrices. And well, the thing is, you get also kind of new building blocks. So these formal partition functions are sort of generating gluings, which I mean, whose edges will be in this case colored. But now you have to add this cylindrical, you know, fundamental cells to glue. There are also physical applications which I mean, and gluing by this is called stuffed maps, because you get maps of maps, and maps is in this case just a word for discrete surface. Okay, I should hurry up then. Thank you. So what's the thing one should use here? Well, just substitute this this smooth manifold. Well, let's say this makes no sense yet. And substitute this infinite dimensional algebra by some matrix algebra. And what you get is the obvious definition, just gauge matrix spectral triple would be this spectral triple product of matrix geometry with a finite part, right? So let's put some gauge fields in there. And then another lemma definition would be that if you extend precisely this this initial matrix geometry by this finite part, and well, this is assumed here from now on to be Riemannian and four-dimensional, and further it will be also assumed to be flat from now on. So these guys, which are used to be interpreted as gauge connection, have also certain fluctuations. So what's fluctuations is the thing we did in this toolkit for higher energy physics. You take this Morita self-equivalence, and this generates your gauge potentials. And so the most general Dirac operator in this notation would read like this, where this L mu and A mu are just commutators with certain skew adjoint matrix. And you have also a piece for the Higgs, but which I'm not addressing quite in detail because, okay. So the field strength is just what you imagine now. This is the analog of the covariant derivative of gauge theory, and then its commutator you can express as a commutator with certain matrix by Jacobi identity, and then you can do a random matrix theory for this matrix. So, okay, so then you analyze the symmetry here. There are a couple of very useful short exact sequences which sort of constrain your group, and you can, I mean, it's more or less credible that, I mean, you should believe that this is true, but actually it's checked in detail because it also matters with the action arc here. And well, this matrix field just transforms in the obvious way. So finally, the spectral action for this polynomial choice. I mean, this is a choice, and initially would suggest that you have a lot of free parameters, but let's see what happens here. Okay, so well, this is just the analog things. Let me just present the result in this tabular form, where in the rightmost column you have the smooth operator. So the analog of these guys would be matrices here. So commutator with a matrix, which is derivation just, and the analog of this gauge potential would be just commutator with this one, and then all these things. Well, this is not part of the. I mean, the bracket should be here, of course. But okay, then the field strength is this what you might recognize? I mean, it's been already defined, but what you see, of course, here is that this non-zero term is present, while in the smooth case, this commutator vanishes on smooth functions. The thing you find then is this thing here, right? So the exact analog of the Young-Mills action. Yeah, so this is the trace on. I mean, you trace operators from this space to this space, right? You do not trace matrices in here, but operators in this space. And this turns out to be this integration has an analog of tracing here in this matrix algebra. It can be identified as follows. So, and you have also pieces which imply the Higgs field, but okay. And this fixes precisely the F4 here to be one. If you want to have normalization, it probably would be related to some coupling constant if you don't. But I made this thing unital. Then the only free things you have here is F2, so which is a little bit in conflict with this, with you having to have this coupling constant here. But then probably you can think of this F2 as the quotient. Okay. That's a not nice thing. A second not very nice thing is that you get some other terms, but this is not very dangerous because, sorry, yeah, thank you. Because it's, yeah, so this, you can evaluate the spectral action at, so D plus the fluctuations minus the spectral action in D, and then this just get rid of these terms. So it's innocuous. So let me conclude then. So spin geometry times a finite path, a finite spectral triple gives you, by definition, an almost commutative geometry, which is very nice and very useful in high energy physics, but it's hard to quantize. Then a matrix geometry, on the other hand, well, it is defined as a finite dimensional spectral triple, which bears also Clifford action, and whose spectral action is computable combinatorially even. And well, then the structure interesting here is just gauge matrix spectral triples, which which yield when you compute the spectral action this PUN Young-Mills theory, if you choose the right path for the algebra. And then the partition function turns out well, it will be then a K matrix model for certain number K large, depending whether you turn on left these matrices that are identified as the spin connection. If you let them in, then you get 17 matrices. If not, then you get 9. Well, that's pretty much it. I mean, so thank you for listening.
Thank you. Any questions?
It's not mine.
In the continuous Con-Shamsuddin construction, an important role is played by the fact that the manifold is a spin manifold. So yes, there is a Dirac operator and everything. Yeah. What happens here? You just do the quadruplication or whatever?
No, I mean, the definition of, I mean, the precise definition of matrix geometry it does have this spin geometry, not only spin C, or not only Riemannian geometry items, but it also has this reality and this chirality stuff. Just I did omit them most of the time because they appear and they're important to solve the Dirac operator, to solve for the Dirac operator of the action. So it's hidden here somehow.
Yeah, but very naively, we have matrices. N by N matrices are your space-time. So they act on a finite Hilbert space,
yeah,
which is column vectors. So what you do, then each element you make it a spinor, which is the quadruplication, the usual quadruplication, or you do something more systematic? No, you just quadruplicate as usual.
Yes, it's C4.
Okay.
C4, yes. Sorry, I didn't get the question. Right. Thank you. Yeah, thank you for clarifying also.
This is just a comment in relation to what Fredeli was saying.
Yeah.
It is, one knows that from 5 dimensions onwards, not from there are manifolds which are not even spin C.
Yeah.
Okay. They have to be twisted by SU2 and so on. Okay. So in some seminar, the question came up, what do you do with that? And he said there is no problem because you can always use the Taylor-Dirac operator, D plus delta, that always exists. Okay. On any situation, the Taylor-Dirac operator, which is used by string theorists, by lattice gauge theorists, very much, always exists. That is enough.
So what does this give you if you plug it for?
Sorry.
What does this operator give you if you plug it in the spectral action?
This is some operator which is a direct sum of several Dirac operators. One acting on the left of the Clifford algebra, full Clifford algebra, the other acting on the right. Okay, so the direct sum of these operators apparently always exists. All the obstructions go away, and you can work with it. It doesn't matter.
Okay.
That was his answer.
Okay.
At that time.
Thank you for the comment.
Any other questions?
Just a very simple question. So this is for something like a flat metric. Right?
Yes. Yeah.
Can you vary the metric?
No, wait. Okay. Would be interesting because this is, I mean, these L matrices need not be the derivative. This might be sort of tetrads. So, I mean, you don't need to identify this as, precisely this analog of the base of the tangent bundle. I mean, which has commuting derivatives. So this might be another thing which might be with tetrads, and that's interesting project also to see what gravitational sector
what you get for the action
might emerge here. But it's much more complicated at this case.
Okay, thank you.
Small model. Thanks. No.
None.
Okay.
Well, if there are no further questions, then thanks very much again.
Thanks.
And we continue 20 past 12. I thought that from the that the spectrum triple doesn't really work there, right? Because some of the Eigen values don't come out correctly. So
This
CP1 works, but CP2 is problematic. So we switch it off.
So okay.